This video will cover the working principles of electromagnetic DC motors. DC motors produce a rotary motion via the interaction between the alternating magnetic field of an electromagnet, called the rotor, and the static field of two or more permanent magnets, called the stator. The electromagnet consists of a large number of closely spaced turns of insulated copper wire. Similar to a bar magnet, a magnetic field with its poles at the ends of the coil is produced as soon as a current flows through the wire. The direction of the charged particle's movement is responsible for the polarity of the magnetic field surrounding the coil. The metal wire consists of an equal number of positively and negatively charged particles, thus it is neutral in sum. In a metal wire, the positively charged atomic nuclei are held in a fixed position and the electrons are free to move, carrying their charge from one place to another. However, the direction of the electric current is conventionally defined as the direction of the positive charge flow. So let's assume the positive charges would move along the wire according to this definition of conventional current. If the positive terminal of the voltage source is on the right of the coil, positive charges are entering the wire at that end, while they are leaving the arrangement at the negative terminal on the left. While moving along the wound wire, the charges flow counterclockwise when looking towards the left side of the coil. According to definition, this is the location of the magnetic north pole. When looking on the opposite end of the coil, the current flows clockwise. Thus, this is where the magnetic south pole is located. You can use your right hand to figure out where the magnetic north of an electromagnet is formed. If you wrap your right hand around the wire or the solenoid with your fingers in the direction of the conventional current, your thumb points towards the magnetic north pole. As soon as the current flowing through the electromagnet is turned off, the magnetic field disappears. When swapping the polarity of the voltage source, the positive terminal is now located on the left, the flow of positive charges changes direction. Now, the magnetic north pole is at the right side of the solenoid, the current rotates counterclockwise at that end. The flow of charges is clockwise at the left end of the solenoid, which is why the magnetic south pole is placed there. When grabbing the solenoid with your right hand from the top of the screen, your fingers point in the direction of the positive current, and your thumb is once again pointing towards the north pole. If a permanent magnet is placed to the left of the screen, with its south pole pointing to the right, the permanent magnet faces the south pole of the electromagnet. There is a repelling force acting between both objects. That force is turned into an attracting force between both magnets when swapping the polarity of the electromagnet. Let's have a look at the same arrangement with the same polarity, but now considering the movement of electrons in the wire. The positive terminal source is still on the right of the solenoid. The negatively charged electrons are exiting the wire at that end, while they are entering the solenoid at the negative terminal. Now you have to wrap your left hand around the solenoid with the fingers pointing into the oncoming direction of electron movement to find the magnetic north pole. Once again, that pole is on the left end of the solenoid, and so there is an attracting force between permanent and electromagnet, As mentioned before, the polarity of the voltage source has not been changed. Now it is indeed swapped. The positive terminal is on the left side of the electromagnet, the negative terminal on the right. The electrons are now moving from right to left in the solenoid, and by using your left hand you can determine that the place of the magnetic north pole has changed with changing polarity, it's on the right side now. According to this, the magnetic south pole is on the left end, which is why there is a repelling force between both objects. The flow of negatively charged electrons rotates clockwise when looking on the end where the north pole is located. Let's prove that rule with a real electromagnet. With the positive terminal on the left side of the solenoid, the permanent magnet is repelled from the electromagnet, while both objects attract each other when swapping the polarity. Coils of a DC motor are usually wrapped around an iron core. Iron concentrates the magnetic field at the ends of an electromagnet. That means the forces acting between electromagnet and permanent magnet are raised by the iron core. However, there is no need for an iron core to make a DC motor work, as we will see some later in this video. Besides the polarity of the voltage source, the place of the magnetic north pole depends on the direction of windings. When moving along the wire, starting at the right end, the windings go clockwise when looking on the right side of the coil. When looking at the side of the solenoid, the wire runs from bottom to top. Let's change that direction of windings. When following the wire again from right to left, the windings are now running counterclockwise when looking on the right end of the solenoid. At the side view, the windings are running from top to bottom. If the positive terminal of the supply voltage is attached to the right end of the wire, you can determine the position of the magnetic north pole by using your right hand. Your thumb will point to the right end. Now, the positive current flows counterclockwise when looking on that end of the solenoid, which is the second evidence that the north pole is located here. The windings of an electromagnet are usually closely spaced, thus a wire with an insulation coating is needed. If you use bare wires, the current will not follow the windings, but will instead cross the solenoid straight directly from anode to cathode, from plus to minus, not creating the desired electromagnetic field. Damage to the insulation may reduce the strength of the magnetic field, since the electrical flow might skip one or more windings. This type of damage in an electromagnet is known as a turn-to-turn fault. With an alternating magnetic field of a solenoid, we will now try to produce rotational movement. There must be a gap for the pivot axis at the center of the solenoid. If a current flows through the wire, both halves of the solenoid can be treated as single electromagnet. Each half's magnetism will be the same direction as the windings. The magnetic north pole is at the left, thus the south pole at the right end of each electromagnet. The magnetic field of the arrangement differs just slightly from that of a single electromagnet. Let's add two permanent magnets to the left and to the right end of the solenoids. In this arrangement, the magnetic north poles of the permanent magnets and the solenoid, as well as the magnetic south poles, are facing each other. Repulsive forces are acting between permanent magnets and solenoid on both ends of the electromagnet. The force vectors are both pointing along the center line of the solenoid, where the pivot axis is located. In sum, the forces are cancelled out. The situation changes if the solenoid is turned clockwise a few degrees. Same as before, there are repulsive forces acting between solenoids ends and permanent magnets ends, but the directions of forces have changed. Besides the partial forces pointing in parallel to the center line of the solenoid, there are components pointing perpendicular to those forces. The force component points upwards at the left end of the solenoid and downwards at the right end. Both partial forces cause a torque pointing clockwise. When releasing the electromagnet, it is spinning until the magnetic north pole of the solenoid points to the right permanent magnet. Caused by inertia, the electromagnet oscillates around that rest position until the movement stops with horizontal alignment. Now, attractive forces are acting between the electromagnet and the permanent magnets. Both vectors are pointing along the center line, thus no torque is produced. Whenever the electromagnet is deflected, the produced torque points back to that stable rest position. To make the electromagnet spin again, the polarity at the solenoid has to be swapped. If the electromagnet is turned clockwise for some degrees by hand, it will spin clockwise for another 180 degrees if it is released. If the polarity is swapped again at the highest point of overshooting, we get a continuous rotation. With a rotary electrical switch, the polarity is swapped automatically by what we get the right timing for a continuous rotation. At this position of the electromagnet, none of the wire ends are connected to the power supply. When the coil is turned a few degrees, both ends make contact, each with a different terminal of the supply voltage. That results in a positive current flowing from that solenoid end marked with a dot to the second end marked with a circle and which is connected to the negative terminal of the supply voltage. With your right hand you can prove that the magnetic north pole of the solenoid points to the top left of the arrangement, same as the wire end marked by the dot. The field of the permanent magnets cause a torque on the electromagnet that points clockwise. If the coil is released, it starts spinning clockwise. At a certain angle of rotation, the switch cuts the coil's current, resulting in the magnetic field disappearing. Caused by inertia, the electromagnet continues moving clockwise until the rotary switch makes contact again. Now, the wire end marked with a dot is connected to the negative terminal of the supply voltage. The current flows from the wire end connected to the positive terminal and marked with a circle through the coil and finally to the negative terminal at the dot marked end. The positive and negative terminals at the solenoid are swept in comparison to the initial state. Accordingly, the magnetic north pole points now into the direction of the wire end marked by a circle. Because the electromagnet has rotated 180 degrees from its initial position, once again the north pole is located at the top left of the arrangement, same as in the initial state. The rotary switch of a DC electric motor that periodically reverses the current direction of the electromagnet is named commutator. The switching contacts running to the supply voltage are named brushes. Early machines used brushes made from strands of copper wire to contact the surface of the commutator. Even if modern rotating machines almost exclusively use solid carbon contacts, they are still named brushes. With the commutator, the electromagnet spins continuously if exposed to the magnetic field of the permanent magnets. The real electric motor also starts spinning after pushing it slightly to make a first contact with the commutator. That need for an initial push is a disadvantage of that simple motor. Another one is that the motor stops spinning when being under load as soon as the commutator breaks the current through the electromagnet. A way around those problems is using another pair of coils arranged perpendicularly to the first pair. The commutator periodically energizes the white marked and the light blue marked pair of electromagnets. Furthermore, the polarity is swept each 180 degrees. Let's define the position with the white marked electromagnets at the vertical position and with the dot marked end at the top as initial state of rotation. That electromagnet is connected to the supply voltage, resulting in a magnetic field being produced. The magnetic north pole is at the top of the arrangement, thus the resulting torque points clockwise. The light blue electromagnet is not connected to the voltage source, thus it has no magnetic field. Consequently, the motor spins clockwise. After 45 degrees, the light blue electromagnet makes contact with the brushes. Consequently, a magnetic field is established with the north pole pointing to the top left. The torque acting on each electromagnet points clockwise. When turned a few more degrees, the commutator breaks the contact of the white coils and the voltage source, thus that magnetic field disappears. Nonetheless, the forces caused by the magnetic field of the light blue electromagnet still point clockwise, making the motor continue to spin in that direction. Whenever one of the coils is disconnected from the power source, the magnetic field of the other solenoid keeps the torque pointing clockwise. There is no point in the rotation where both electromagnets are disconnected from the voltage source. Let's swap the polarity of the brushes next, thus the right brush gets connected to the positive terminal. With your right hand you can determine that the magnetic north pole of the light blue electromagnet points downwards by now. The resulting torque points counterclockwise. Same is for the white marked electromagnet whenever it is energized by the commutator. There is a continuous rotation pointing counterclockwise. Let's prove the predictions with a real motor once again. Note that the copper wire is wrapped with same winding for both coils. When going from left to right, the wire runs from top rear to bottom front, same as in the animation sequences. That's also true for the blue wire forming the second coil. As predicted, the motor spins clockwise with the positive terminal at the left brush of the commutator. Even when stopped under load, the motor continues spinning as soon as it is released. What happens if one of the electromagnets is wound in the wrong direction? On previous animations, the wire ran from bottom to top at the front side of the light blue coils when going from left to right along the wire. Let's change that direction so that the windings run from top to bottom at the front view. Same as before, the north pole of the white electromagnet points to the top, causing a clockwise movement of the motor. As soon as the light blue electromagnet gets energized, the rotational movement is slowed down. With your right hand you can determine that the north pole of that solenoid points downwards, causing a counterclockwise rotation. The motor oscillates instead of producing rotational movement. Even 3 electromagnets are sufficient to make an electric motor spin continuously. At the commutator, each end of each coil is connected to one end of the nearby coils. The commutator switches from one electromagnet to the next, each 60 degrees. For a short interval, 2 coils are energized simultaneously. Once more you can determine the position of the magnetic north poles with your right hands. As you can see, the resulting torque on both electromagnets points clockwise. If an electromagnet is at the upper half of the screen, its magnetic north pole points to the top whenever the coil is energized through the brushes of the commutator, while the resulting torque points clockwise. If the electromagnets are at the lower half of the screen, their south poles point downwards, causing a clockwise torque too. Finally, you can prove your knowledge about DC electric motors. The windings of the solenoids of the motor shown here run counterclockwise when looking at the top and following the wire from the dot marked end to the circle marked end. The negative terminal is connected to the left brush of the commutator. What's the rotational direction of the motor considering the movement of negatively charged electrons? The first thing to be considered is: what is the direction of electron movement at the front side of the vertical solenoids, from left to right or from right to left? If your thought was from left to right, you are correct. The second question to be answered is: what hand is needed to determine the position of the magnetic north pole? Your left hand is the right answer. When trying to grab the solenoid in such a way that your fingers point into the direction of electron movement, your thumb points to the magnetic north pole. Where is that pole? You are correct if your thought was downwards. Finally, you have to determine the resulting torque. The lower end is pulled to the right, the upper end to the left. Thus, we have the answer to the question. The motor spins counterclockwise. That's all about DC electric motors for now. You get more information and some exercises about those machines on the project page. Thanks for watching and I'll be back.